Assalamualaikum warahmatullahi wabarakatuh and a very good morning. My name is Nurul Amirah binti Ridwan, and today I would like to present my final year project entitled Conversion of Glycerol into Glycerol Carbonate by Heterogenous Biochar as Catalyst under supervision Dr. Zati Ismah binti Isha. The growing industrialization and rising demand for alternative energy have led to the abundance of biodiesel-derived glycerol that can cause a danger to both environment and economy. The abundance of glycerol must be turned properly and efficiently into valuable product in order to contribute positively to the biodiesel economy. Glycerol is a well-known molecule with several paths of conversion into thousands of important fine compounds such as 1,3-acropendiol, acrolein, glycerol carbonate GC, and other compounds through several reactions such as oxidation, hydrogenolysis, acetylation, transesterification, steam reforming, and esterification. Conversion of glycerol to GC have paid significant interest for researchers in the past 5 years. Among desired products, GC can serve as a value-added chemical and has excellent properties such as chemically stable, non-flammable, and low toxicity. Glycerol can be converted to GC through transesterification reaction. Transesterification reaction is the reaction that is utilized to transform one ester molecule into another ester compound in the presence of alcohol, either under acidic or basic conditions. The utility of heterogeneous base or acid catalyst for transesterification reaction has been widely reported due to their ease of separation, lack of corrosion or toxicity, and environmental friendliness. Biochar is a heterogeneous catalyst that is a carbon-rich solid formed from pyrolyzing biomass with little or no oxygen, and it may be applied to soil for agricultural and environmental benefits. This study was to shed light of the factors that affect the effectivity of catalyst specifically in the transesterification reaction of glycerol to GC. Next is problem statement. Despite the surplus of glycerol, the abundance of wastes generated from the palm oil industry also shows a significant increment every year. This has become an issue for the oil palm industry because it will lead to a waste management problem and uneconomical biodiesel production plant. Less study can be found on using biochar catalyst based on oil palm biomass for transesterification reaction of glycerol to GC. These knowledge gaps constituted for starting point for experiments in this study. The three objectives of this study are to study on the pretreatment of OPKS biochar using sodium hydroxide, to characterize the porosity and surface area of treated and untreated OPKS biochar, and to evaluate the performance of treated OPKS catalyst in catalyzing transesterification reaction of glycerol using TLC. These are the three journals reported that has used different type of biochar as catalyst in their studies. Sheikh Khaliev 2021 was used biochar prepared from cow dung and fish scale as a catalyst to compare the effectiveness of both catalysts. The temperature for transesterification reaction they have been used was 85 degrees Celsius with the duration of 60 to 90 minutes. They used FTIR, BET, SEM-EDS, and Hammett indicator for the catalyst characterization. Next, Mohammed and Ahmed 2020 used a plant-based biomass prepared from reed plant as a biochar catalyst to undergo transesterification of glycerol to GC. The reaction was run at 40 to 80 degrees Celsius with the duration of 30 to 150 minutes. They used FTIR and BET for the catalyst characterization. And the third one is Wang et al. 2017 used meat and bone meal as biochar catalyst with the reaction condition at 65 degrees Celsius for 150 minutes. For the sample preparation, the samples was washed and dried at 105 degrees Celsius for 24 hours. Then, the OPKS was ground into powder and sieved to make sure the powder is uniform in size. The powder was divided into 3 different crucibles that were calcined at 500, 600, and 700 degrees Celsius for 90 minutes each. After that, the 3 samples that has been calcined at 3 different temperatures was treated with sodium hydroxide for catalyst activation. The samples then filtered and washed with deionized water until the pH is 7, then it was dried at 105 degrees Celsius overnight. Next is transesterification reaction of glycerol to GC. The 3 next round bottom flask reactor were equipped with a condenser and 1 thermometer attached for monitoring the temperature in flask. The flask then put in paraffin oil bath over hot plate with magnetic stirrer steering. The reaction condition used was at 120 degrees Celsius for 180 minutes for each catalyst, which is the treated 500, 600 and 700 degrees Celsius. The catalyst and glycerol was added and mixed together until the temperature reached to 120 degrees Celsius, and the urea was added with the ratio of glycerol and urea 1:2. Then, the characterization of opic acid catalyst was tested by using first Hammett indicator, which is to determine the catalyst basic strength. 25 mg of catalyst plus 1 ml of Hammett indicator solution plus 1 ml of methanol was mixed together and wait for 2 hours to observe the color changes. Phenolphthalein will change the colorless to pink color, shows the basic strength is 8.2, and 4-nitroaniline will change the yellow color to orange, so the basic strength is 18. Second, the samples was analyzed by using SAM-EDX to determine the morphology and the element involved in the samples. Third, FTIR was used to investigate the sample's functional group. And lastly, TLC was used to monitor trans-esterification progress. The solvent system used was ethyl acetate and methanol with the ratio 4.4 and 0.2. The KMNO4 solution also used to visualize the chromatograms. KMNO4 solution contains 0.5 gram potassium permanganate, 3.33 gram potassium carbonate, 0.83 ml of 5% sodium hydroxide and 50 ml of distilled water. Next is results and discussion. First, thin layer chromatography or TLC. The comparisons between glycerol spot and the sample spot shows no difference, so the hypothesis that can be made is the spots presence on TLC plate A, B, C, and D was corresponds to glycerol. According to Balsal et al. 2008, the spot of glycerol they have been observed was in the same pattern as shown in the figure 1 that represents to glycerol. Next is results and discussion of FTIR. The results show the spectrum for uncalcined, calcined 500, 600 and 700 degrees Celsius. These results determine the functional group for that could be observed after calcination at different temperature. Based on the figure 2 and table 1, the peak for OH stretching frequency for uncalcined was centered at 3196.07 cm-1. After calcined at 500 degrees Celsius, the peak was slightly shifted to 2924.29 cm-1 and shifted to 2867.75 cm-1 after calcined at 600 degrees Celsius. The samples for calcined at 700 degrees Celsius shows no peak for OH group. Anisuzama et al. 2015 has studied that the calcination at 550 degrees Celsius to 650 degrees Celsius, the GC yield was increased steadily. At temperatures over 650 degrees Celsius, GC yield may have decreased slightly. Therefore, the higher temperature could affect the effectiveness of catalysts for the production of GC yield. The hypotheses that can be made from these results are the calcination at 700 degrees Celsius might be too high and cause the sample to lose the moisture and affect the frequency of OH group that corresponds to water. Working calcination temperature for the catalysts are in the range of 450 degrees Celsius to 650 degrees Celsius. The hypothesis can be supported by further characterization using SEM. Based on the SEM or SEM results for calcined 700 degrees Celsius, the biochar catalyst was more porous and has a smoother surface compared to biochar that calcined at 500 degrees Celsius and 600 degrees Celsius. After that, this is the spectrum for calcined 500, 600 and 700 degrees Celsius and treated 500, 600 and 700 degrees Celsius. These results determine the functional group involved after treated with sodium hydroxide. OH group for the spectrum of calcined 600 degrees Celsius was shifted and located at a lower frequency compared to spectrum for treated 600 degrees Celsius from 2867.75 to 2589.82 cm-1. This could be related with the previous study where Lee et al. 2021 analyzed the ground coffee residue biochar GCRB that has a greater intensities of IR peaks of OH stretching corresponds to alcohol compared to the ground coffee residue biochar with sodium hydroxide activation GCRBN due to the highly hydrophilic surfaces of the GCRB. This is the spectrum of reaction 500, 600, 700 degrees Celsius and treated 700 degrees Celsius. The samples was analyzed after undergo trans-esterification reaction of glycerol with urea to produce glycerol carbonate. The presence of OH, CH, and the CO group was corresponding to glycerol functional group. The presence of glycerol shows that there are no peaks for functional group of glycerol carbonate compound. This has been proved by TLC test where there is the presence of glycerol spot on TLC plate. Next is the results for SAM, which is to determine the morphology of catalysts. Figure 3 A, B, C, and D that correspond to uncalcined calcium 500, 600 and 700 degrees Celsius respectively has a highly irregular and undefined surface structure. The structures were clumped and not uniformly distributed pores. Small particles of ash were also spotted on the surface of the OPKS biochar. Figure 3 E, F, and G show a well-defined porous structures with corresponds to treated 500, 600, and 700 respectively. The supported journals stated that the same pictures of the carbonated fish meal at 650 degrees Celsius shown in the article shows that the material is very porous. Therefore, the results shows that after catalyst calcined and treated with sodium hydroxide, the morphology started to become more porous and well-defined. For EDS results, first is the results of uncalcined, calcined 500, 600, and 700 degrees Celsius. The results determine the difference of calcination temperature towards the weight percentage of element involved in the samples. The weight percentage of carbon for uncalcined is 73.46%, increased to 85.70%, and decreased to 79.12% after calcined at 500 degrees Celsius and 600 degrees Celsius respectively. The percentage was increased to 90.5% after calcined at 700 degrees Celsius. The weight percentage of oxygen was decreasing from uncalcined 21.03% to 14.30%, 15.89%, and 7.94% after calcined at 500, 600, and 700 degrees Celsius respectively. According to Hafiz et al. 2021, the calcination of the mixed cement paste at 600 degrees Celsius improved the decomposition of hydration products, caused the decrease of oxygen compound because of the decrease in hydration. Next, the results of uncalcined treated 500, 600, and 700 degrees Celsius. The result will determine the presence of sodium after treated with sodium hydroxide. The treated 500 degrees Celsius shows the increase of carbon weight percentage from 73.46% to 79.25% and slightly decreased to 78.12% for treated 600 degrees Celsius sample. Then, the percentage for 700 degrees Celsius was increased to 95.33%. The percentage of oxygen decreases from 21.03% to 17.66%, then 16.73% and 4.67% for uncalcined treated 500, 600, and 700 respectively. The percentage of sodium for treated 500 degrees Celsius was increased from 0.69% to 1.27% for treated 600 degrees Celsius. This can be supported with journals where the study of ground coffee residue biochars with sodium hydroxide activation (GCRBN) shows that it have a 20% higher of sodium compared to ground coffee residue biochar (GCRB). One possible explanation for these observations is that sodium absorption on the GCRB surface occurs often during sodium hydroxide activation. For the conclusion, the pre-treatment of OPKS biochar using sodium hydroxide has been done in order to activate the biochar catalyst. The porosity and surface area of treated and untreated OPKS biochar was determined by using SAM EDS instrument. The porosity and surface of the samples before calcined was complex and started to become porous and well-defined after calcined and treated with sodium hydroxide. EDS results shows that the higher the calcination temperature, the higher the weight percentage for carbon, and the lower the weight percentage of oxygen. The working temperature for calcination was in the range of 450 degrees Celsius to 650 degrees Celsius. The performance of treated OPKS catalyst in catalyzing trans-esterification reaction of glycerol has been evaluated by using TLC. The TLC spots corresponds to glycerol spot and not GC. The product, which is GC, could not be achieved due to the error that might be happened during the experiment. As a recommendation, further study should be done on testing the samples with Bernard and Met-Taylor BET to identify the specific pore sizes and the porosity of the sample. The results will help in the study to make a comparison of the pore sizes between the samples at different treatment and to investigate which condition is the most suitable for an effective catalyst. Next, the sample of reaction 500, 600 and 700 degrees Celsius should be run under some EDX for the better observation regarding the effectiveness of every treatment. This analysis could help in investigating the morphology and element content in the sample. After that, trans-esterification reaction of glycerol with urea should have been done in a closed system to avoid the excess water come out from the condenser that can affect the error in the reaction. I think that's all from me. With that, I thank you.